All right, so this might be one video. I might split it up into two. We're going to go over panel data. Be a lot more work in state than there usually is, but we're going to do some. The slides are a few, not near as many as what a typical week would be, but we'll do a lot more work in data. So, excuse me. So let's get going here. So, when we're working with panel data, this is going to be data that we have collected not at a single point in time, which was going all the way back when we were talking about different types of data sets we mentioned was kind of cross-sectional data. But this is going to be data that was collected on the same subjects, right, for multiple points in time. So a good example of this, I think I've got some the data set we'll use where we look at student test scores, but they follow them over time. So they have what their standardized test score was in 2006, 7, 8, 9, et cetera. Now, we're going to talk about and investigate the difference between what we call balanced and unbalanced panel data. So balanced panel data is that for every single student, I've got them recorded in all 4 of these years. Right? So every single subject, student here, could be countries, right, that we have information on over several points in time, could be companies, right, whatever it is, we have the same years recorded for every single observation, right, no missing values there. So that would be called balanced panel data. Now, if we have unbalanced panel data, right, that might be that for some students, students move in and out of state school districts, maybe only have them for 2 of the 4 years. Another student, I have 3 of the 4. Another, I have 4 out of 4. So this is what we call as unbalanced panel data. Well, we can actually relate this to what we were talking about with the last week's material, which was missing data. Because essentially with an unbalanced panel, we just have missing data. Now, we're not concerned if this is completely random of the types of students that we don't have all 4 years collected on, or the type of subject we don't have all time periods on. However, if we've got missing data that's correlated with either our X or our Y variable, so here we don't have like a regression yet, but we're talking about test scores. If for some reason, students that tend to not do as well, we see maybe they aren't as likely to be tested in subsequent years. Maybe they're more likely to be put, moved to a different school district, different state, right? Maybe they're more likely to get extra help, right? And in which case, maybe they can take, some type of additional test. So they just don't take the standardized testing data, or sorry, test score. They won't be in our data. So essentially, an unbalanced panel, we're always kind of worried about missing data issues, right? And are those missing values, is the reason why it's unbalanced, is that correlated with the X or Y value we're looking at? So kind of consistent theme, connecting these two themes together, an unbalanced panel data set is essentially, we might be concerned with some missing data that's correlated with our X and Y values. Now, let's think about if I've got panel data, and I'll kind of keep using my student example, maybe I want to know what's the impact of the class size, so I could do X as class size, on the performance on this standardized test. So my test score data is Y, and I somehow have collected the class size of every student as well. Well, those things are going to change year to year, right? It might be in a larger class or smaller class in different time periods, right? But there's going to be some things that don't change over time. So we're going to call that Z, right? So notice here with panel data, and we don't typically write this out as much, but our kind of standard when we're looking at cross-sectional data, if I can get this to switch over to the dot cam here. Oh, why isn't it liking this? Oh, 9, why? I just have to do this. So, zoom out just a little bit. I thought I had this set right, but it's a little bit too big. So we don't usually write this, but like in our standard regression, we're really saying like each Y and X value are really going with a specific observation. Like, so for individual 1, what was their class size and test score? For individual 2, what was their class size and test score? When we have panel data, we're going to have the same subjects, right? But we've got multiple points in time. So our observations are not just specific. And here I kind of had my error term also, in any given observation exist. I now have the time period that that observation is in as well. Okay. So let me see if this is just a little shaky there. There we go. So we now might have these factors that, yeah, maybe my class size and test scores vary from year to year, but the underlying students like IQ, right, that may not change, or the family income of that student is consistent across those time periods, or the school that they're in is consistent across those time periods. So what we're then going to do is say, well, we want to control for all these things that we would call our, sorry, not T, I here. So just to rewrite this to be clear, are going to be time invariant, right? They're specific just to that subject, right? So these are going to be, you know, quite often we don't have data, right? We talked about not having important omitted variables. There's going to be a lot of things that we can't collect on students, but they stay consistent over time, right? Maybe this is something like students' race, right? Or like I said, they're in the same school district, or maybe this is they're in the same income bracket, right? Their family's in the same income bracket. Now, those things could change over time. I'm using some that have a little bit of time invariance to them, but we're trying to control for factors that basically are the same across all time periods for that subject. Okay? So in order to do that, right, I kind of have this, so we'll kind of walk through. Let's say I had 2 different years. So I just have 2 different time periods, and I've got some characteristics about the student that I don't think change over time. But I have this class size that does change from year to year that they're in, and their test score performance changes from year to year. Well, if I simply were to run both of these regressions, right, I could come up with the estimated effect of class size, but it would be for a specific time period. I want to estimate the effect of class size across every single time period, right? I want to have as large of a sample size as possible. I want to like run this regression with all of the years included, not individually for each year. So what I can do, right, is instead of running this regression on Y, I'm going to look at the change in Y. Right? So just think about if I had this equation for year 2000, year 2002 and year 2001, if I was to write that out, well, notice I've got kind of beta 1 in here for both time periods. I've got beta 2 here, but notice this doesn't change over time, so this would always cancel out. So what I'm left with here is what we call a first difference regression. If I, instead of running regression of the Y variable on our X variable, I look at the change in the Y variable and run a regression where I'm looking at the change in the X variable, well, that would completely eliminate any time invariant factors. Anything that's consistent across that subject, in my example, students across time, would be completely eliminated, or essentially we'd be controlling for it, right? Even if we don't have data on it. So by looking at these first difference regressions, we might get very different coefficients for the size, or sorry, very different values for the size of that coefficient beta 1. Right? So this is one of the solutions we have. We brought this omitted variable problem a lot in class. This is one solution we have to it. Okay, so let's see what this kind of looks like in Stata. And it might seem like we're not using, you know, here we're not just running this year by year, we're using all of the data. So I've got my global set here, and this isn't going to be right, so we'll open it up once and then I'll get my global to be right because I'm on a different computer here. So this is, what do I have? First differences, I think, is the first regression. So let me highlight this. I'm going to change my global so that now hopefully the rest of this do file will run just smoothly, right? So I've got that first difference data set opened up, and this had that kind of grade size. I guess I didn't do class size here, I did grade size. But I was also looking at what was this change in their total score, was their standardized test score. I think we looked at the data. I might have kicked out some of it just to make it easier. I did, but this total score was basically, the total score that we had, and you see all of this, was their combination of like their math and reading score. I believe this was ISTEP data, so Indiana standardized test score data. So instead of like simply running a regression where I look at total score, spell in 2007 and grade size in 2007, and I would kind of do this for 2006 as well. So if I run this regression, I can come up with a coefficient on that grade size, right? So it's going to reflect a 1 unit change in grade size. So having one more student, the impact that would have on their total score. Now, the problem is I've got a huge omitted variable here, which is all of the other factors that, would predict that student's test score. So if instead I create these new variables, right? So I'm going to take this as the total score in 2007. So in this data, we had their grade size in 2006, total score in 2006, grade size, total score in 2007. I'm going to create these new variables, which are the change or the first difference in total scores from 2007 to 2006, grade size from 2007 to 2006. And notice here, okay, the grade size of this student changed by 4. And as a result, their test score changed by 12. So I'm now going to run a regression with these first difference variables, right? Or the changes in these variables. I will now see, oh, well, before it looked like the effective grade size was positive and statistically significant. The reason why this result is much more reliable, remember, grade size change, well, what's a 1 unit change in that variable? It would be if I went from 1 year to the next to a class size of 1 person higher. So it's the same unit change we had before, and it's just going to change my predicted test score. The change I would see in my test score is now going to go down by 0.013. However, the added thing I get to say here is, before I wasn't holding anything else constant. When I run these first difference regressions, I'm holding all time invariant characteristics of that student constant. Now, anything that might change year to year, so maybe, my family income might not be a good example because their family could switch income brackets. Well, that's not time invariant. I would still have that important omitted variable. However, anything like student's race, I'm now controlling for that, right? That's not changing year to year, okay? Okay, so this is going to be a much more reliable coefficient, right? We're adding on this additional term, which is holding constant all other time invariant factors. We couldn't say that before, okay? So we can't control for time invariant factors here. Those could still be some omitted variables, but we can control for time invariant factors, things that are consistent across time, okay? All right. So go back here. Whoops. So that was kind of our first difference regression. Right? In fact, I think since I already talked about it, we'll stay in data here. And I've got a second data set, which is looking at this player shot data. So this has like every single player in the NBA. I think this is NBA. It might be. No. This is NCAA basketball data. It looks like it's for the time periods of 2019 to 2022, right? And it's going to have every individual, their height, what their year they were in school. This is like the proportion of free throws, I think, that they made. This is the proportion this is their average free throws that they make. This is like game by game data. So here's kind of their attendance. So notice for some of these players, right, we've got 3 years. Some of them I've got for 4 years. Okay. So it looks like if I were to use this data set, and I think it's got what division they're in attendance, but notice, even if I ignore these missing data values for now, let's say I had information for every single one of these players in every variable. How can I test to see if I've got every player for all 4 years? Well, I can very quickly here look at the data and see that isn't the case, right? But let's say I had like, I don't know, a data set where I had 10 years of data, I had countries, and it wasn't quite clear. Some countries I only had information on for 9 years, others I had all 10. One thing that we can do is if we generate this variable, I'm just going to call it count variable equal to 1. So it's just going to put a 1 in there for every single observation. I'm then going to say, okay, by this player ID variable. So player ID, it looks like a name. This is one of those things though, where I encoded the data so that every name has a specific number attached to it. So by this player ID data, I'm now going to create this total seasons, which is just the sum of that variable that's always a 1. What that essentially will do is for each player, tell me the total number of seasons I have them for in my data set. So I'm going to go ahead and run that. Now, very quickly, I can see, oh, man, this is unbalanced, right? I've got some players for 1, 2, 3, 4 years. If it's not as obvious to me just looking at the data, I can then kind of look at just tab out that total seasons. And I can see here, well, I've got a pretty unbalanced panel. For 36% of the players, I only have them for 1 year. For 9%, I've got them all 4, you know, et cetera, et cetera. So this would be evidence that we have an unbalanced panel. Now, if I go back, I could actually do this for my test score data as well. So here, generate this count variable equal to 1. Now it's going to be by sort. And let's see here, what's the variable? Master ID. So this was just the student's kind of assigned a number. I'm going to, and here we need to be careful. We're going all the way back. Something we talked about, the difference between EGEN and GEN. EGEN is going to allow this sum function to add up across all values for this master ID. If I use gen sum, it's going to kind of do like a running total. So I always want to use EGEN here when I'm checking to see if it's a balanced data set. And then I put total seasons. We'll call this total years for the students. So I want to look at what that total years variable is. Okay. So I'm going to count the observations, right? Here, I think this is going to be an easy one because I only have everybody for 1 year, right? And I say happen for 1 year, right? The way the data was kind of set up, I had each year as a separate variable. Okay. And I'll kind of check some future data sets. We'll kind of keep on looking at this to see, is it balanced? Is it unbalanced? Okay. So the next thing that we're going to talk about is, okay, I can run these first difference regressions, and I can do that if I have more than 2 points in time, but there might be an easier way we can do this, okay? So let's think about this same kind of setup where I've got panel data. So every observation is specific to a person and a time period, or a country and a time period. And this could be yearly, could be monthly. We know that there's going to be some factors that are time invariant, okay? So if I just kind of move this over here, hopefully you can kind of see, well, really, what is this going to do? Everyone, if I was trying to make predictions for Y, and here I think I can draw something out for you that'll help with this. So let's say I had that, and it looks something like, the marker already died on me here. YT, oh, come on. One of these markers will work. There we go. So let's say I've got these time invariant factors, and then I have this variable that I'm really interested in estimating the relationship between that and my Y variable. Well, really what this is doing, if these are time invariant factors to every single person in our example, well, it's almost like what we could do is create a dummy variable for every single person, right? So if I, for instance, had, you know, person 1, a dummy variable, person 2, a dummy variable if the observation came from them, et cetera, et cetera. Well, it's really like I want to estimate different intercepts for every single person. That's what that time invariant factor is going to do. So I could just include a dummy variable for every single person here. Now I have to be careful, right? Just like with any other categorical variable, I need to include a dummy variable for every single person except for I need to leave one of them out, right? Now, we're not as interested in what these coefficients are as much as we are just making sure we're controlling for these time invariant factors specific to every student or every person here, okay? So here what we're thinking about is I just want to include a dummy variable for every single group, and then kind of n minus 1, I have to leave one person out, right? So yn minus 1, I've got to have a comparison group, right? My intercept still needs to be specific to, right? Who, I have to have some reference group, right? So I have to leave one of those out, okay? Let me think if there's anything else I want to say here. I think that should kind of cover it. So how do we do this in status? Before we kind of, well, yeah, we'll look at stata first, and then I'll kind of mention how it's related to averages. That might make a little more sense for us here. So I've now got this birth state, birth data by state. I'm going to open that up. So it looks like I've got every single state. Looks like there are 6 different years. I've got the number of births, average age of the mother, and average birth weight. So one thing I could do here real quick is check to see if it's balanced. So I'll create this count variable. Then here I've got a problem. My state is text. So I'll show you what happens if I try to do this with this variable. So by sort state, egen total years equals to the sum of my count variable. If I try to run this, it's mad, or oops, that's not why it's mad, but oh, well, it actually looks like it was able to do that. It was able to kind of treat this text or identify this text. So if I'm using that by sort command, right, I can use this text data. I don't have to encode it, okay? So I don't have to have like a number like I did with the other data sets. I can use, what word am I looking for? Why am I blanking? Alpha, I can use not numeric values, right? I can use qualitative variables. Sorry, there we go. That has actual text. There you go, text instead of a number. So I could then say, okay, do I have all of these states? Do I have them all for 6 years? Well, I'll kind of tab that total year variable I created. Sure enough, I've got all of them in here. In fact, here I could kind of estimate, oh, I don't have 50 states. Looks like I've got 51. Oh, yeah, I've got Washington, D.C. I've got the District of Columbia as well, right? So I could run this regression, right, where I'm looking at the average birth weight on the average age of the mother, right, or average age on mother in years. Looks like for every year older that a mother is, the birth weight of the baby goes up, right? Now, there's going to be factors, right, across states are different. Different states have different incomes. They have different racial demographics. There's just going to be different laws that exist across states. So maybe those racial demographics, the income variable, maybe that doesn't make as much sense because that changed a little bit, year to year. However, there's going to be things like state laws that we know are very different, right? So we know Utah versus New York, those laws are going to look very different. So what's one way we can control for those time invariant factors? Well, we said first differences could work here, right? I don't have this data set up as nice as I did before. So how do I take difference between, we'll talk about that in a second where we could do first differences. But probably an easier way to do this in Stata is going to be simply using that idot command. Remember that idot command took every single one of those specific values for that observation of state, and it included a dummy variable. Now, here's where, okay, it's telling me I can't use a string or a text variable. So what do I need to do? I need to use that encode command. We've used this before, right? So I'm going to create a new variable. I called it state FE for state fixed effects. So this is the variable that I want to use in my regression when I use that idot. It needs to be not text or not a string variable, but it needs to be a number or numerical. Well, it looks like it's still text, but remember when it kind of turns this to blue, if we click on it in the data, we can see, oh yeah, every text line of or string of text will actually be given its own number. So now I can run this regression where I include a dummy variable for every single state. So now controlling for every single state, it looks like the effect of being 1 year older actually decreases birth weights, right? And that's much more reliable or unbiased of an estimate because I'm holding constant any of the time invariant factors that exist within these states, okay? All right, so just to kind of show you some other ways we can run fixed effects in Stata. I don't love this one, because I have to always worry about kind of encoding my variable, but also it shows me, it shows me all these. Well, if I've got 50 states, that's fine. If I looked at my student test score data, so the data set I had, actually to every single student in Indiana, if I create a dummy variable for every single one of those, it's going to be like so long. I have to scroll up forever just to get back to my regression, to the variables that I'm actually concerned about. So what I can do is use this built-in areg. So what areg does, it's the exact same thing as this idot command. It's going to include a dummy variable for every single observation, or sorry, for every single unique response that we could see for this variable, but it's not going to show me all of those dummy variables coefficients. So if I go ahead and run this, okay, I get the exact same coefficient. I get the exact same standard error, test statistic, right? However, it's going to absorb all of those dummy variables. It won't show them to me. Now, that's great, right? If I don't care about them. If I do care about them, for instance, if I wanted to make a prediction for what is the expected average birth weight of a state that's the mother's average kind of years of age would be, I don't know, let's say 32, and they're in Utah, well, I don't have my coefficient for Utah. I can't make that prediction. That idot command gives me those coefficients so that I could make predictions for what the predicted birth weight was for mothers, for states that have mothers of a certain age, and then also specific to that state. All right, there is another way of doing this. So you'll kind of see with these fixed effects and kind of this panel data, there's a lot of different ways of doing this. So another one is, and this will become kind of helpful for some things that you would do kind of after this class, but we can set this up and tell Stata this is a panel data set. So right now, it treats every data set the same when you open it up or kind of load it up into Stata. What this XT set will do is it says, okay, tell me your two variables, right? So we can't use, once again, if I tried to use the just regular state variable, I think it's going to get mad at me here if I remember correctly my syntax rules. Yeah, you can't use string variables. So we didn't really get around that. We still are going to have to use that encoded version of the state variable that has a number associated with every single state. But this XT set says, okay, I'm telling you this is a panel data set, and my subjects are this first variable. So my subjects are this state number, right, or state name, we can think of it as. The kind of second variable is going to be, okay, here's my subjects. I have them collected over what variable represents the time. Here for us, that would just be year. This could be month, this could be day, depending on the data set. For us, we've got panel data sets where we have collected data on 51 different states, including DC, for 6 different time periods. So I've now I'm telling Stata, this is a panel data set, and that now gives Stata some additional commands that we can use, and it knows how to use those with a panel data set. So if I, instead of using reg, now run this xtreg, so that's telling it I want to run a regression with a panel data set, I can still run that regression of average birth weight on the average mother's years of age for that state. But instead of using idot or a, kind of with this, that absorb command, if I put comma fe, that tells Stata to run a fixed effects regression, essentially include whatever I told it was the subject. So here, the state, I've got 51 different subjects across 6 different time periods. It includes dummy variables for every single value of that variable you told it was represents your subjects, right? So now, what do I get? Exact same coefficient, exact same standard error, statistical significance. Now it gives me some other stuff that we're not going to worry about for the sake of this class, right? But it does kind of highlight there are some additional statistics that this setting it up as a panel data set would provide me. Right? But ultimately, we could run any one of these regressions and obtain that same coefficient. And in all three of them, we're controlling for these time invariant factors. Okay. Now, may not be as clear, but what we're thinking about when we include these dummy variables, in a weird way, it's like I'm saying, okay, on average, right, what would the predicted Y value be for person one? And then allowing this X variable to change, then what would those predicted Y values, how much would they also change by? So including these dummy variables, it's essentially like controlling for what the average of each person's test score was. And then as that grade size changed, or as that other variable changed, it impacted how much Y changed by. Well, here, we didn't have the test score data. We had birth weights. So what we're going to do, instead of creating these dummy variables, really what a dummy variable does, remember, well, we'll kind of think about the most simplistic one. So let's say I had Y. We'll go back to non-panel data just to make this point. We said if I was trying to graph out this relationship between X and Y, if that dummy variable was equal to a 0 and X was equal to 0, beta 0 represented like the intercept value for that 0 group. And then we would kind of have whatever beta 1 is, that would represent the relationship between X and Y. Right? Now, we also had that second group where if this was a 1, but X is still 0, we said that dummy variable is really capturing the fact that even if the relationship is the same, and we talked about we can do interaction terms if it's not, but here we're assuming it is, it could be the same relationship that exists between these two groups, but one of them is going to start out at a higher amount. So this could be something like, we know that the impact of, what's a good one? Increase in the years of education on predicted income. That might look kind of similar between both, males and females, right? The effective education is going to increase the predicted income for both groups, but we know there's discrimination that exists. So if we're thinking about males being the one group, maybe their kind of starting point is a little bit higher. So all we're really doing is saying that there's a difference in the average of these two groups, right? What is that difference in the average? Beta 2. So we instead, and I wouldn't suggest doing this, these are a lot easier ways, but just to kind of conceptualize what these dummy variables are doing, I'm going to run this line of code where I say, okay, by each one of these states, right? So by this state fixed effects ID I created, that was that numeric value, create a variable which is the mean of the birth weight for that state. So it's taking the mean of the average birth weight across all 6 time periods, right? I'm doing the same thing, but for the mother's age down here. So I run these 2 lines of code, right? By each one of these states, create what their mean birth weight and their mean age was across those 6 years. So kind of notice here, for Delaware, they're going to have a mean, right? That's the same for every single year because it's the mean across those 6 years. DC has a different mean, Florida has a different mean, etc. So I now have the average within that state for these 2 variables. I'm now going to create these 2 variables, which simply take, okay, let me see if I can get this to all be on the same string. No, I can't. Where are we going? There we go. We're saying, okay, take that state's birth weight from that year. So it gets kind of weird because we have averages here. That was the average over just that single year that was across individuals in that state. But take the birth weight for that state. Where is it at? Yeah, right here. And subtract the birth weight mean. And then take the mother's years of age from that year in that state and subtract that state's average mother's years of age. So I'm going to create those 2 variables where I'm essentially, what we would kind of call this is, and I put it up here, demeaning both of the variables. So we'll calculate the mean for each subject, right, across time. And then for each time period, we'll take the value of that variable for that year and subtract that group's mean, or we're demeaning the data, okay? So now I can kind of run this regression where I've got the birth weight, I call it birth weight minus, I left out average here. So it's the birth weight demeaned and age demeaned. So it's really, we're kind of looking at the same regression, birth weight on the average age of the mother. But by demeaning the data, we've essentially done fixed effects, right? So we get kind of the same coefficient here, okay? So if we go back up here, where was that? Yeah, 33.4. Okay. Let me think if there's anything else I want to say here. I think that's it. All right, so yeah, that's it. All right, we keep having the same number of observations, so that's good. So let's keep going down here. Oh, other thing I wanted to point out, it's not as easy to see here, but when we're looking at these different regression results, depending on if you use some of these different methods, you'll notice kind of your R squared values. Whoops. So they're the same if we do IDOT or that areg command, because those really do the same thing. The R squared, that starts to be kind of weird once we get down here, because when we're really running fixed effects, we're looking at multiple types of variation that exists across subjects, but also within subjects, but also across time and also between subjects. So our R squared becomes a little bit more complicated. We're not going to dive into those issues. So if you're looking at these results and you say, oh, R squared looks a little bit different when I'm demeaning the data versus the R squared value I'm seeing when I use these kind of IDOT commands. The reason why is because that IDOT and the areg commands don't allow me to identify the different types of variation that exists. So this is just like the total variation across time and across subjects. Here, when I'm running that demeaned or that fixed effects regression where I've set it up as panel data, I can now start to get, well, how much variation is explained between subjects, across time, et cetera. But we won't dive into those issues. I just wanted to kind of point that out as long as we had all that up here. All right, so that took us down to here. Right? Now, another thing that we can do is not only can I control for factors that might vary across, factors that might not vary within a state, I can also control for factors that might not vary within the same year. So if I had my regression and I've got, this was like birth weight and mother's years of age, we were just talking about ways that we could use fixed effects to control for kind of time invariant factors, right? Or things that were specific to, so in our example, this was state, right? So things that do not vary within a state, right, across time. So they were time invariant. They're the same in that state across all points in time. There might also be things like, oh, I don't know, in 2009, there was a recession. Well, that impacted every single state. Or maybe there was a national law passed that impacted every single state. So what we're also going to have, right, and here, what am I going to use? Not Z. Oh, I don't know. What letter do I want to use here? So X, Y, Z. We'll just use, I don't know, H. Why not? So this is going to be things that are not time invariant, but in a weird way, we can think about this like subject invariant, right? Or in our example, this would be the year, right? In any given year, these laws impacted every single subject the same. So we can control not only for state level fixed effects, we can also control for time or year level fixed effects. So we'll call this kind of a two-way fixed effects model. It's really simple to do this, right? Now, I can do this using my IDOT command, or I could really do two IDOTs if I wanted to. However, we want to get used to kind of setting these data sets up as a panel data set. So I'm going to do the same thing I did before, where I say, okay, oh, here, what do I want? No, this isn't actually what I want. Yeah, so I set it up a little bit different. We'll kind of, I think I'll change this so that it matches up with what I was doing up here. So before, what were we doing? We did state fixed effects, and I was telling it, though, within the same state, these things vary across years. So I'll kind of show you this both ways. So if I were to simply run the fixed effects model, right? When I set my panel data up this way, remember the dummy variables it was including was for whatever I told it the subject was. So this would be state dummy variables that get included, or it's going to control for things that were time invariant within that state. So that's what we were doing before. If we want to add in also that there were things that were subject invariant, or that kind of were the same across subjects but varied across the years, I have to use that kind of IDOT command here, right, to do my two-way fixed effects. So here, I'm going to run this regression. What I now have is I'm not only running these fixed effects that were including dummy variables for every state that I can't see, I now also have a dummy variable for every single year. Now I get a much different estimated, coefficient for that relationship between years of age and birth weights. Now, I could get the exact same results if instead I had set this up the other way. So maybe I'm thinking, okay, I've got years, and for every single year, I've got 51 states, right, including DC. So I'm just going to copy this to make my life a little bit easier. I don't have to type as much. So now, if I've set the panel data set up this way, probably doesn't make quite as much sense. I don't know, think about usually we've got like every state, we've got 6 years collected for it. We usually wouldn't say I've got 6 years collected in 50 states for each year, but we could set it up this way. Now, including that fixed effects, it's not going to include state dummies. Remember, I've now told it that first word in XT set is my subject, so it now has year dummies, right? But I could also use the IDOT command to include dummy variables for the state as well. So if I run this regression, I should get 3.75, I get the exact same result. Now, which way should I do this? The whole reason why I had it actually set up this way initially was to show you, like, if you do it with states, you just have to look at more dummy variables. Looking at your data, you had 51 states in only 6 years. So which one do you probably want to get absorbed just so you don't have to look at as much? You probably want the thing to get absorbed is what has more, more value. So here we had more subjects than we did time periods. Okay. All right. So that would be kind of our, where are we at? Two-way fixed effects models. Where did we leave off here? I was showing you this stuff here. This is just kind of proof when we're thinking about using that demeaning method. If I were to write out y as a function of x, and then the mean of y as a function of x, right? And kind of here, here was kind of the average. So if I took y and I subtracted the average y, I can just plug in these equations. It simplifies down to, I can actually run this regression by just looking at the d mean value of y and the d mean value of x, and it will give me the exact same thing. So it's going to absorb all of those dummy variables, right? So this is just kind of support why we could do that, right? And we looked at that already in Stata. Okay. I think I'll end this video here. I've just got more examples that we'll kind of work through in Stata, and then also look at one other topic, which is autocorrelation. So I'll end this video here, kind of make it the second video to replace Thursday's class.